the functional safety workload of the internal IP and NPU within the large automotive IC through the analysis and emulation usage for software-based safety mechanisms. The abstract. As the number of semiconductors used in the modern cars dramatically increases, the safety is becoming the dominating factors in the automotive semiconductor lifetime. Achieving the desired safety level is burdened by the runtime of the fault injection and data management during the fault campaign. And this paper describes the process of data management and fault injection, run optimization, and the reduced time they achieve the desired safety level and the product certification. This paper gives a case study of the fault campaign flow for internal IP NPU in a large automotive IC using the emulation for software-based safety mechanisms. Section Introduction. According to the ISO 26262 standard, functional safety is the absence of unreasonable risk due to hazard caused by the malfunctioning behavior of the electronic systems. Safety manager handles hazard analysis and risk assessment (HARA). At this stage, each hazard event (HE) is assigned with the automotive safety integrated level ASIL based on the severity of the classification, such as potential harm S, probability of the operational situation E, and the controllability by the driver or other traffic participants C. Then the HAE safety manager define the safety goals and set the functional safety mechanism requirements needed to fulfill those safety goals. During the product development, the functional safety requirement comes down to the technical safety requirement and further to the hardware HW safety requirement and software SW safety requirement. Based on the assumption of use, a certain IP inside the automotive SoC which contributes to the certain safety goal is assigned with the needed safety requirement. The safety mechanism SM are integrated into IP and are intended to verify the associated safety mechanisms. To prove the effectiveness of the SMs, the diagnostic coverage DC is measured. The DC expresses the capability of the SM to discover the faults and is calculated by dividing the number of the failures detected by SM by the total number of failures in the electronic systems. ASIL determined the single point fault metric SPFM and the level of the coverage provided by SM for single point fault and the residual fault. For example, to satisfy the ASIL B, SPFM greater than or equal to 90% is required. Table 1. Table 1 is the SPFM value for each ASIL. After the SM information with the expected DC and the detected protection area is defined, the fault campaign process continues to identification of the alarm net and the no observed net. The next step is to determine and generate the test scenario followed by fault injection. The workflow of the fault injection has 3 steps. First, generate the fault list. 2. Inject the fault list. 3. Report the metric. The Siemens provide a small flow for the above steps and the single functional safety database and FUSA DB is used throughout. And the IP is the NPU section 2, NPU safety verification with the safety mechanisms. The NPU IP figure 1 is part of the Automotive SoC contribution to safe video sensing. The NPU provides fast and energy efficient hardware acceleration for AI and ML applications in computer vision, imaging processing, and other domains where state-of-the-art deep learning networks are used. NPU consists of several processing unit blocks, processing blocks in PU0, PU1, and PU2, memory access block MEM, and the controller block CTRL. And the safety island is designed to manage and monitor all of the safety content with the automotive SoC. In particular, Fault Manager Unit FMU in Safety Island collects fault and reports related safety event information. The list of SMs, Table 2, is defined by Safety Manager is statement of request for verification. So typically memory parts are protected by the parity of ECC SM9 to SM13. Related fault signals are connected to FMU directly, while logic parts often require software-based SM like self-test SM2 and SM3, where a form is needed to control the intended function, so the formula checks the behavior and asserts the fault signals. The majorly FC fault campaign for the safety mechanisms protecting memory parts was done in using a simulation flow. This paper deals with the function fault campaign for a software-based safety mechanisms, which was conducted using an emulation flow. The goal was to verify the DC defined the level of the 90% ASIL B, considering the margin of the error of the 1.21%. The expected DC should be greater than or equal to 91.21%. Failure in time FIT rate metric proportional to the number of transistors in the die was used. Based on FIT rate distribution for logic and memory parts of each block inside the NPU, the expected DC for each block was estimated, so it was decided to use the SM3, Table 3, SM1, SM2, Table 4 as mandatory SMs and the other SMs additional as their contribution to the overall DC score is insignificant. For SM3, which protect for all blocks B, expected DC was set to 91.21%, and for SM and SM2, which protect CPU inside the controller block, the expected DC to the 16% was sufficient. The final DC for NPU can be calculated by the weighted average of the DCs for logic and memory parts. Figure 1, block diagram of NPU with related SM. Table 2 is SNS targeted for emulation and simulation. Table 3 is expected DC for SM3 self-test. Table 4 is expected DC for SM1 and SM2. The Section 3, Emulation Methodology. To facilitate the fault campaign for complex software-based safety mechanisms and to make a DC verification feasible with an achievable time, hardware-assisted verification tools like an emulator are required. Since emulation was one of the options to be used for the functional verification of the NPU, it is easy to add additional scenario for the target DC with the existing emulation verification environment. If the target design is big and the scenario needs to be long, the emulation fault campaign is the best option in terms of runtime. To set up the environment of the fault campaign, the fault list generation, a fault injection run, and the database fault list is the result requires. As few separated steps for a fault campaign are required. Siemens closed loop tool chain is chosen for NPU FC. The fault list is generated by the safety scope faulted RTL and the fault detected netted FDNs are the input to the compiled DB. The generated fault list is stored into FUSA DB. Compilation by Veloce refers the FUSA DB for the fault list and the file for the FDN and FDNs are those nets whose nets are stored during the golden run and compared during a check run. There are two types of FDNs, alarm and observed net. Alarm net is a signal that a SN can recognize when there is a safety violation. Observed net is a signal that the Veloce can recognize when there is a safety violation. The Veloce fault app is used to inject fault on the fault list. Finally, the result of the fault injection run is stored into FUSA DB. Workflow is presented in Figure 2. Figure 2 is a fault campaign using an emulation flow. The outputs of the compilation are fault injection net, FIN, and the block synthesizes the fault Veloce emulator. FIN, which is an output of compilation, will be double of the fault net in the FUSA DB because the Veloce assigns stock S0, SA0, and the stock at 1, SA1 on the fault net. Only permanent faults are considered as A0, SA1. Other fault types like transition fault and etc. are also supported but beyond the scope of this fault campaign. If the FUSA DB has n of the fault net, the output of the fault list of the compiled DB will be 2n due to the S0, SA0, and SA1 for each fault net. Some faults can be optimized out at this stage. There are several types that do not require the fault injection run. Veloce provides the optimization method to increase runtime performance by speaking fault injection run. That logic. If the fan-out of the FIN does not have any reader, it means fault impact cannot propagate it further. This logic can be optimized as that logic. No port in memory. In a design, if there is a memory then the address is readable anywhere, there would be no way to design is affected by injecting fault. Memory which is not read well anywhere will be optimized as memory, no read ports in the memory, and FIN and FDN. If the fault that is defined as FIN and FDN both by user, this fault net will be optimized as FIN and FDN fault. IDs are assigned to each FINs after compilation, not including the optimized net. This ID-based FIN provides easier fault injection and run environment setup. The FDNs are captured during the execution of the test scenario on the emulator, and the results are saved as reference values golden run, and the golden run means normal run without a fault impact. So this run will record the all behavior of the FDNs to be referenced. Then each fault from the FIN injected during the execution of the same test scenario and FDN for this check run are compared against the reference. Figure 3. So as a result of the check run, the alarm can be detected or undetected. The fault can be observed or unobserved, thus giving 4 cases DO, DU, UU. Check run means the run where the fault impact can be observed for or the detection by the comparing them against the golden run. The number of faults to be injected can be used. The check run are based on the executed on the emulator in parallel. At vector analysis, the fault nodes are checked with the nodes with the constant values are optimized from the injected list of the four for this testing scenario. Just to save the time more, it can achieve the fast forced injection runtime by excluding unnecessary time such as system initialization time. The initial state of the DUT before trigger signal can be saved for golden run and restored for each check run. The figure 3, golden run and check run. During the fourth injection run and no additional runtime is assessed necessary after the alarm is detected and the observed net is observed. By applying the early termination feature, the fast time can be also achieved based on the number of the DO cases. Finally, the results emerged for the test scenario for the given SM, and they are classified and used for calculation of the ASIL and FMEDA metric. If the score is not enough, then the test scenario is regenerated and the fourth campaign is restarted. A. Generation of test scenario for fourth campaign. Typical test scenario for fourth campaign includes the following steps. Post-boot CPU. For step 1, post-boot CPU. Step 2, CPU activated watch timer WDT. Step 3, CPU triggered command scheduler CMNS to start operation. Step 4, CMNS configures internal blocks. Step 5, CMNS controls internal blocks which read input, process data, and write output. Step 6, CMNS waits internal blocks end. Step 7, CPU gets interrupt from CMNS about operation end. Step 8, CPU triggered the MEM operation to generate the CRC and release CRC generated by internal blocks. Step 5. Step 9, CPU compares CRC with the reference. Step 10, the comparison fails. CPU sends interrupt alarm _fail. Otherwise, step 3 to 9 can be repeated. 11, if all operation end, CPU sends interrupt alarm _path. 12, CPU stops WDT. If the WDT triggers before the CPU sends pair or pass or fail interrupt, CPU sends interrupt alarm hand. It is also possible that the CPU makes a CRC comparison once after all operation end. The test scenarios for the FC must meet two conditions, both high quality and short runtime. High quality means that if test scenario does not satisfy the above metric, it should be regenerated. To get a DC greater than or to equal to 90% required for ASIL B, one should make the test scenario with the quality above the sign-off level of the test scenario used for functional verification. On the other hand, the test scenario used for a function verification often cover each function with redundancy, so it takes a long time to run all test scenarios. However, test scenarios for the FC should also be used for error detection in the actual field test, and those scenarios should be completed in short time because they should not affect the actual software operation. So there is no simple method to make an ideal test scenario. There is an accurate and a combination but a slow method through the analyzing IP specifications and algorithms and adding features one by one. The following points can be considered to generate high-quality test scenarios more efficiently. The test scenarios used in real software does not have DC as high as expected. In general, software safety function scenarios do not utilize the IP functions depending on the scenarios required by the system and IP functionality and may be active or inactive. On the other hand, the test scenario used function verification often cover each function of the redundancy. It takes long to run all test scenarios. However, test scenarios for a FC fault campaign should be used for error detection in the actual field test, and those scenarios should be completed in a short time because they should not affect the actuals of their operation. There is no simple method to make an ideal test scenario, but there is an accurate and confident but slow method through the analyzing the IP specification algorithms and adding features one by one. The following point can be considered to create high-quality test scenarios more efficiently. For the one, is test scenario used in real software does not have a diagnostic coverage as high as expected. In general, software safety function scenarios do not utilize all IP functions. Depending on the scenarios required by the system, IP functionality may be active or inactive. Okay, I read this two times. If the certain functions of IP continue to inactive, those functions can be excluded from the diagnostic coverage measurement range. However, software engineers generally do not guarantee the IP features will continue to be inactive. This is called because the function can be activated again depending on the scenario. So now one should provide a test scenario satisfied a higher DC compared to the test scenario used in the software. In general, the obtained result DC and the diagnostic coverage and achieve ASIL B and is needed to utilize all minor functions in addition to the main function of the IP. So the test scenario used in functional verification can have higher diagnostic coverage. 2. As the starting point is advisable to the measure DC for the test scenarios, the functional verification. In a lucky case, it is possible to achieve ASIL B with only those scenarios. However, the case is rare. If you achieve the ASIL B with the test scenarios to get a long time, it is possible to rank test scenarios by the total coverage and remove duplicated test scenarios. It is good if the contributing the test scenario satisfy the DC, diagnostic coverage, and the execution time. Otherwise, the optimization is required. 3. If the test scenario for campaign duly generated, it should be able to detect both the system hang and data mismatch by a fault. In particular, if the IP has a chain of the multiple sub-IPs and the fault is injected into sub-IP in the form of the part of the chain, and the familiar is not propagated, then there is usually cannot be changed by the configuring the sub-IP and the back of the part of the chain. To solve this issue, one should configure each sub-IP that they can react sensitively to small fluctuation caused by the fault. As the change by the 1 bit is required, the intermediate value like hexadecimal 0888 and 7FFF are more advantageous than extreme values like 000 and FFFF. The fault is injected into register or a port by the 1 bit, so the test scenario should be able to detect the fault causes by the changing in a single bit. If the value is extremely, the fault may not be observed. Extreme values are likely to cause data saturation while changing by 1 bit due to their small variable range. On the contrary, configuring the values to be intermediate is effective in the preventing data saturation while changing values by 1 bit, because the variance range is larger than the extreme values. It is often safe if the system performance is degraded due to the fault. In general, the performance improvement IP such as cache may only reduce performance without system hang and data mismatch when fault is injected. If the performance is important to the system, one should define a test scenario at the system level that should catch the difference when the performance is not satisfied. Therefore, faults can cause only performance difference can be found at the system level, and the IP itself is considered to be safe. B. Debug methodology. The most important part of the fault campaign is the result analysis to meet the target diagnostic coverage. For UU case, the engineer must use the expert judgment to define whether it is safety fault or additional scenarios are required. And software and the hardware method can be used to find how a fault propagated in the system. Using a software method in code linking, the expectation is that a monitor of the core CPU may capture the regions while the fault propagation is hidden. Also, comparing the waveform fast triage between the golden run and checked run can be of the approaches based on a hardware to figure out where the fault propagation is masked. By having these debug methodologies, engineers can find the debug point and more scenarios to get expected DC. UU analysis. Non-injectable net based on a synthesized information vector quality are already filtered out by the compile DB of MyGNet, and by applying the vector analysis VQC, the classification of fault injection alone with the injectable net is needed based on the resolution report. The following three methods are used for this fault campaign: fast triage, configuration check, and the read transition check. True, a fast triage logic. The main concept of the fast triage is to find out how propagation by injected fault cannot be spread out and where the propagation is reached out to the alarm net and the observed net. The result of the fast triage can be classified as a safe fault with the expert judgment based on the evidence why the fault effect is not propagated. Since the Veloce supports the utility to compare two waveforms easily, deviation between the golden run and check run can be found as long as the set waveforms are ready. By comparing the port of a hierarchical modules from the fault injection net (FIN) to the alarm and the observed net (FDN), the deviation can be found. The deviation between the golden run and the check run is found on the output of module 2 and the figure 4, while no deviation is found on the input of the module which has been alarm net, which can be a safe fault. But because the fault effect is not propagated the alarm net, then they can assume that there is a logic which blocks the effect of the fault propagation as module 2 or module 1. The golden run and check run and figure fast triage concept. Sorry, what's different? Yeah, this is one of the cases why the deviation is by fault propagation cannot be found. The deviation on out underscore A was not found because the value underscore A, X, and Y in the golden run and reference run, check run was same with the current test scenario in figure 5, while there were there were some toggled values on value A underscore A X Y in the golden run, and the value AXX was stored at 1 in check run. However, when the value of the value underscore AXY in golden run was 1, which is the same as the value in check run, so it can be safe fault because there was no deviation between golden run and check run. Figure 5 is the snip code for UU case. The configuration check is there with the ARM core. If the core has a safety mechanism as ECC or parity and a fault is injected on the cell, the configuration needs to be checked whether the safety mechanism enabled or not. If the ARM core is not familiar, it is hard to debug on the waveform or software code. If the safety engineers can have both access to software code and a synchronized waveform at the same time, it is helpful to check the configuration environment such as the enable ECC, parity, and watchdog. If the safety engineer is familiar with the waveform, the engineer can trace back the software by moving waveform time frame back and forth. If the safety engineering is familiar software, the engineer can use point on software so that waveform show the current status of hardware. So the codeling which Veloce application can support this methodology. Read transition, check, memory. For the case of injection of fault on a memory cell, the fault cannot be propagated through several receivers unless the system reads the data from cell. To prove whether the fault propagation effect on the receiver or not, the address and the read address cannot be needs to be verified. In the case of figure 6, read transaction can be checked with the value of the neighbor NA. If there is no transaction with the current test scenario, it can be safe fault because the injected fault cannot be propagated further. The figure 6 is simply code for lead transaction. Section 4, the result and analysis. The fault campaign required several iterations before the expected diagnostic coverage was achieved. After each iteration, one should analyze the UU cases and generate test scenarios and rerun the functional safety. Fault campaign. The analysis of result and update of the test scenarios, the PU0, PU1, and MEM. The NPU architecture, data flow, and the algorithms were analyzed, and the above-mentioned modes were supplied to the such iteration table 5. Namely, at least those steps were taken. First, step 1. After checking the bit with the proposed by sub-IP, the special data patterns were created for the customer's MSB and the other, or 0, and for the letter MSB 0 and others, or 1. Second, step 2, if there was 2 or more inputs for the affected output of the sub-IP, then the special data pattern was applied to only to one input. The data for others was simplified so that the value changed by one bit can propagate to the end of the IP change. Creating the input data in this way increased it so that the sensitivity to the fault injected into special data patterns, making it easier to generate output failures. The NPU IP has an activation failure using the LUT for non-linear functions, and the operations using LUT have a chain structure. If the several LUTs are used in the test scenarios, then due to the injected faults of the values of each LUT of the chain can be very variable, resulting in a considerable data saturation. To prevent this, the target LUT was set for each test scenario, and all other LUTs were bypassed, so the test scenarios were created in a way that minimized the influence AUT. Step 4, the result of MAC is combination of multiple multiplier and adder. If the result is configured to be only positive or negative, only negative, and the data saturation is often expected due to clipping. To avoid this, input data was created so the input data also generated intermediate values. For example, the output data assigned value 0 was created at the sum of positive value and negative value. The output data can improve the data sensitivity by default because it can increase the range of the outputs that can be changed by the input. Then number 5, the to-cover register logic additional test scenario was created. Value 0 and value or 1 were consecutively written and read and compare and mismatch. Written and read and compared. Written or read and compared. Mismatch indicated an error due to the fault. The scenario was more efficient in terms of runtime compared to normal test scenarios for register where random values were used. Table 5 is percentage of due for SM3PU blah. After updating test scenarios, formal analysis was used to check the count of influence of the remaining UU cases. The faults which were the outside of a COI count of influence were marked as safe fault. Then the to increase DC diagnostic coverage, more expert judgment was applied to the remaining UU cases. The fault of the spec out feature is safety fault. The hardware features not included in software scenarios were ejected in the ejected in the IP, then the fault injected in the related module and register and port, and etc. were marked as safety faults. Spec out. Second, the fault of the debug feature is a safety fault. Debug features such as the performance monitor and internal counter for the debug do not affect the IP. So the released fault was marked as safety fault. Debug. 3. The fault of the clock gating disabled feature is safe fault. The fault which disabled the clock gating logic instead intended for power reduction does not and so they were marked as a safe fault. The gating of the clock simply the disabled feature is a fault. The fault which may disable the clock gating is logic intended for the power reduction does not affect the output, so they were marked as a safe fault. The fault of the individual range bit is a safe fault. The valid range of the register for the fault may be limited depending on the scenario. The fault of the invalid range does not affect the output, so they were marked as a safety fails configuring. The fault of the range bit in the safety fault. The valid range of the register or port may be limited depending on the scenario. The fault of the embedded change do not affect the output, so they were marked as a safe fault configuration. The fault of the performance feature is safety fault. Features that only increase the decrease performance do not affect the system hang and the output data mismatch, that they were marked as safety fault performance. The analysis of result and update for test scenario for PU2. The PU2 itself consists of the several parts. To get the high score, test scenario should cover all of them, including the computing core, memory command scheduler, bus, and memory access blocks. At the first iteration, real software test scenario was used, but it is only touched to arithmetic logic, partially some related register, and almost none of the other registers like control and other logics. Then the test scenario from the functional verification was applied. It includes all arithmetic logics, but the memory operations were not enough, so they were added also. 4. After further analysis of the UU case, it was found that access some register has specific patterns on the if it was added. Table 6. Percentage of 2 or 4 some FM3 PU2 block, and E. Result of the fault campaign. The final diagnostic coverage was calculated as sum of the DODU compile, omit that logic reporting the COI and the safety, safe, divided by the difference of torque, divide and compile. Dials coverage, DU compile, and COI safe and fault list. The result of the fault campaign and SM3 are shown in the table 6. The final suit for SM3 includes early optimized test scenarios with a high efficiency and low turntime. Table 7. Result of fault campaign for SM3 self-test. The result of the the safety fault campaign, SM1, SM2 CPU part are shown in the table 7, and the SM1 software test library STR and custom test scenarios were used for SM2. Only test STR was used. Proper configuration setting checked with the code. As the number of the test scenarios provided, the ARM is limited. Analysis result, additional analysis of the remaining CPU cases using the debug methodology with code mentioned earlier is planned for our future work. Table 8. Result of the FC for SM1 and SM2. Summary. 5. Summary. The functional safety workflow for NPU IP with a software-based SM is probably presented. The internal block was related SM1 of selected based FIT rare latest distribution. The FC process, including the fault injection run by the emulation, was applied. Debug methodology for efficiency UU analysis were introduced. At each FC iteration, after the detailed analysis, the RP architecture and fault test scenario were updated, and final some remaining were fault were classified as safe. The all target diagnostic coverage score of 91.21% necessary to the ASIL B metric was achieved. For education of the test scenario runtime for optimization of the test scenario runtime for software safety verification can be included in future work. Reference. Thank you for your time. Today I read this paper, Functional Safety Workload over Internal IP NPU with the large automotive IC through the analysis of the emulation usage for software-based safety mechanisms. Thank you again and see you next time.